Okay, so let's do a recap. We're gonna have a quite busy and I think, my opinion, fascinating lecture today. Okay, first thing first. We'll see. Yeah, may or may not disagree with me, but what's interesting. So last time we basically completed the discussion about curvature. We discussed the curvature tensor, and last time we introduced the Bianchi identity. R sigma mu plus rho R sigma lambda mu plus lambda sigma R lambda rho mu is equal to 0. And shall we introduce the Riemann Ricci tensor, Ricci scalar, and the Einstein tensor G mu nu, R mu nu, and R G mu nu, and we show that the Bianchi identity can be written as W mu G mu nu is equal to 0. We discussed several examples, and we spoke about the geodesic deviation. A squared delta x mu, and the tau squared is R mu rho sigma alpha dx rho over the tau sigma over the tau delta x alpha. That basically tells us how the difference delta alpha, if we have two geodesics, x alpha plus delta x alpha, how do they change to nearby particles? And then we did the most important thing, which we said that now it's about time to derive Einstein's equation. So we derived Einstein's field equation. R mu nu minus 1/2 R G mu nu equal 8 pi T mu nu, which was derived basically as a generalization of Poisson's equation. Questions before we move on?
Poisson's equation is the equation we had last time.
Yeah.
But this equation don't have any derivatives in it.
Can you say that a little bit? How do you get into R?
So that they are inside, not explicitly written.
It's fine. Okay, we're going to have a lengthy discussion about that in 1 minute. So before that, if you have any other questions.
I have a question about parallel transport.
Yeah.
It's related. So we can define parallel transport of some vector along the curve, right? And how to call this derivative?
Full derivative has
Yeah,
separate spaces.
it has to be 0, right? If we
And the vector is not supposed to. I mean, the whole idea is that the vector does not change when we go.
yeah,
This is the mathematical definition of not the vector is not changing.
yeah. But if we want to calculate the parallel transport along a curve that's closed, like a loop,
Yes.
the same. But
gave this example, right? Let's say this is Earth, and I'm taking a parallel transport of a vector going along this path. Right? What happens is that I'll end up going back to the same location, and I find out that the vector after getting to the closed loop will not reach the same. If I compare the vector right, at the end of the parallel transport, will not be the same as the vector originally. The idea of a parallel transport is keeping the vector constant with me.
Okay, so
And the difference, we know what the difference will be. It's exactly going to be the curvature.
along each of these lines, the vector is constant, right? I mean, it's
Vector is parallel transported, meaning I'm not changing the vector. I'm not changing the vector. I'm taking it with me, and I'm making sure that it's, when I transport it with me, I'm taking the vector, I'm making sure that it is parallel to itself.
But what we can say about its components? Are they changing?
Of course they change.
But the length, let's say, of the vector is not changing.
So, parallel transport of a vector. Yeah, the dv mu, dv over d lambda. Fine, it's d v and mu over d lambda. Plus gamma mu sigma rho. Sigma over d lambda. V and v rho. So this has to be equal to 0.
Okay, so we have 3 lines, right? 3 paths.
V mu is the
to make a
component.
loop,
V
right?
mu is the component of the vector. It's
Yeah.
one path. Doesn't matter, right? I can select the path. Whatever. This is A. This is B. This is C, which is equal to A. Doesn't matter. I'm taking the vector along whichever path I take, while keeping it constant. That's what it means. Then I'm asking myself, okay, what's going to happen to how is the vector going to look like? I can simply integrate over that. What I'm going to end up with, if the space-time is not flat, then the difference in the vector, right, will be curved. That's exactly the meaning. Which I did not prove it to you, I told you you can prove it at home, that this you get the same result. This is what we did when we took the difference in the vector, the change in the vector when I go from point A to B along two different paths. I told you could, if you get from A to B along this curve, this path, and then from B to A along the different paths, you will get the same result. So how the vector changes, how the components of the vector change, like that. If it's infinitesimal change. If it's more, then you have to do the full integration over. But they will change. Of course, they will not be the same unless R is 0. Okay? We have to think a little bit more about it. Fine. You can always do the parallel transport of the vector, and the Riemann tensor is exactly what tells you whether the space-time is flat or not, based on the outcome that you get for an infinitesimal transformation. Okay. Let's go back to Einstein's field equation. Let's go back to Einstein's field equation. So now I'm going to answer your first question. said we got that from a generalization of Poisson's equation. Now let's verify. 4 pi g. This is Poisson. Classical. This is a GR. So there are many things to say about this equation.
This is the heart of G.
This is general. You can only admire. What you have here is something that tells you what is the distribution of matter. What is here?
Curvature.
It's curvature. So this is really a geometry. So Einstein managed to connect two seemingly completely independent concepts into one concept. We said this is exactly what tells you how the existence of matter acts to curve space-time. Well, it's an extremely difficult equation because to get R, the Ricci scalar and the Ricci tensor. This is of course the Einstein tensor. And then need to first derive the Riemann tensor, then contract it. You have the Riemann tensor. The Riemann tensor is made of the derivative of the affine connection and times the two affine connections, plus the two affine connections multiplied. And the affine connection itself is made of the derivative of the metric times the inverse metric. So we have two derivatives of the metric in sine, which makes it extremely difficult. In fact, what we're going to do from this point on until the end of the semester is to look for solutions to this equation. We understand, study the solutions. We really only study two solutions. That's what we have time for. Not the third solution. One solution in vacuum. In fact, there is one solution which you already know, which is don't know black holes. Minkowski. 0 equal to 0. If there is no matter, then there is no curvature. Minkowski flat space-time. It is a solution.
But it's
I need to ask myself what is the boundary condition. I can say the same
Zero,
about
it's a zero everywhere. Okay, of course, this is not a very interesting solution. We're going to learn about another solution, which is called the Schwarzschild solution. And then it's a solution for Einstein's, it's another solution for Einstein's equation in vacuum, namely this times that is cool of presenting the gravity of stars and also limits to black holes. There is another solution which we learn, which is where this is not zero. It's called the Friedmann-Orbital-Walker solution, which is a solution that describes the entire universe. So there are simplified assumptions of how the distribution of matter in the universe is. We can make another solution to that. It's a different solution. It presents, eventually will lead us to kosmology, which is a different branch of physics, and concepts such as a black hole, etc. Big Bang, etc. So the real Big Bang, not the TV show. Okay. For the meantime, how many equations do you see here?
66. But it's symmetric.
Yeah, it's symmetric, right? So if it's symmetric, then how
10.
many? 10, right? See that? If it's symmetric, then everything, you know, is should be equal. So there are 10. In fact, there are less because we have the Bianchi identities, which is written here, give us 4 constraints. So in fact, there are 6 independent equations. So answer the equation, we can say because of symmetry, plus Bianchi, gets us to 6 independent equations. As we already said, these are extremely difficult to solve. And in fact, we don't know all the solutions. Possibly, we don't know that we know the solution. It could be, very well be that there are other solutions that nobody has found. And actually, there are people who dedicate their professional life to find solutions. They're not linear. What does it mean that they're not linear? Solutions. That means that if we happen to already know two solutions, a linear combination of them is not the third solution. Okay? Unlinear equation. Extremely difficult. What do I want to say? Okay. That's about it. Now there is one fascinating issue that nobody of you have said anything, which is not surprising because you have to look at it very carefully. This is not a unique equation. You can actually add some term here without affecting anything. Which ones we could add? I mean, remember when we derived this equation, the requirement was it was a physical requirement, right? Conservation of energy, which we wrote as T mu nu, comma nu equal to 0. Right? So we could add another term here, which will not contradict that. Right?
Add some 0?
No. If I had here a term which looks like lambda G mu nu, that's not going to contradict that, because when I take the derivative of that, it's going to be 0, because why? So the metric compatibility, the derivative of the metric is 0. So I can add this term here.
It's like shifting the energy by a constant.
Pretty much, yes. In fact, Einstein added this term. Which, you know how we call this term?
Cosmological.
It is a cosmological constant. So this lambda known as the cosmological constant. Now, of course, this is an equation, so it doesn't have to be here. You can simply put it instead of here. You can put it here. Then it has a different name. It's the same thing, just have a different name. Here it's a geometry, and here it's a matter. So how do you call it? You know, isn't it? Dark energy. Why would Einstein introduce it? It was Einstein's idea to put this. You know why? It's a story about history of science.
That's the solution for the universe.
No. First of all, the universe is not empty. The universe is, we have stars. It's not a vacuum like, you know, it's not an astronaut that's just hanging there in space. There's nothing's wrong. But yeah, it's related. At the time, when Einstein introduced his equation, this was 1915, this was 110 years ago. At the time that Einstein introduced his equation, it was believed that the universe is static, not changing in time. It was there forever and it will be there forever. But Einstein, when people started to solve this equation, people realized that there is no solution that leads to a static universe. This equation by itself leads to a universe that is expanding. So Einstein broke his head what to do. And you realize, okay, if I can put some constant here, given the right value, it will cancel out exactly, then the universe could be exist. Of course, it's a very bad idea because why would this constant have exactly this value? Then what happened?
People discovered that
This was Edwin Hubble,
yeah,
astronomer Edwin Hubble. 12 years later, 1927, he discovered that the universe is not static, the universe actually expands. That is, the story says, Einstein said, this is the biggest mistake of my life. Because his equation would predict the expansion of the universe 12 years before the universe was actually discovered. So he had a prediction, which he just threw away. So just took away this constant and say, okay, my mistake, sorry, should have. That was 0.29, so it was 14 years ago. Now, okay, so during the most of the 20th century, this was just a fun story. Then what happened in 1999? 70 years later, after Hubble was dead, of course, Einstein was dead, 70 years later, what was discovered? By the way, using the Hubble Space Telescope, named after Hubble, you don't know, the universe is not only expanding, but is accelerating expansion. That doesn't make sense. Why that doesn't make sense? Because gravity always pulls, always attracts. So you can imagine a situation where there was some initial condition, boundary value that caused the universe to expand, but then the universe should contract because of gravity. Now, why would the universe expand? It seems to be like the more vacuum there is in the universe, the more expansion you have. It's completely counterintuitive. There is nothing even remotely close to that in everyday life that we encounter. And what happened? Why would the universe expand?
dark energy.
Because there is a dark energy. So there is some energy. Now, it's not the same minor correction. If you look, about 70% of the total energy in the universe today is here. Which nobody has any idea what it is, where it is coming from. Now, it's even more, even stranger than that. Because if you look at quantum field theories, for example, there is a prediction that there will be a vacuum energy. Now, I believe none of you have ever learned quantum field theory. I think so. Now, in principle, this is an extension of quantum mechanics. And in quantum mechanics, even if you go to the ground state, in quantum field theory, the vacuum is the ground state, it's the lowest. Ground state, there is energy to the ground state in quantum mechanics, which is what? What is the ground state energy?
Of what?
Anything.
What kind of
Anything. Harmonic oscillator.
H bar omega.
Half H bar omega, right? And the same thing goes to quantum field theory, basically replacing particles with fields, and then the vacuum has fields, and they're all in the ground state. Right? Basically. And the ground state there is energy. So we'd expect to be some sort of energy in the vacuum associated. And in fact, theory tells us what this value should be. So say lambda should be of the order of Planck mass, quite very powerful. Planck mass is a very high mass. It's 10 to the minus 5 grams, it's 10 to the 19. Okay. So this is a theory, this is theoretical prediction. This is not surprising at all, simply there is this thing which is called vacuum energy. It's fine.
It's M4 of what?
To the 4. Max Planck to the power 4. MP is a mass, Planck mass.
Okay.
No one Google it. There's a thing which is called a Planck mass, and this is basically related to unified forces. So this is the energy scale which all the different forces are uniform. Okay, so what's the problem then?
It's wrong, probably. If you're saying there is a problem, probably it's not what we see in the telescopes.
Exactly. So we see the telescope. We do see that there is an acceleration in the universe, from which we can calculate that there is this dark energy. We don't know the source, but okay, maybe it's something related to this vacuum energy, random fluctuations in the vacuum energy, which has to give us some sort of energy. So what is the problem then? So what's the difference between the observed and the theoretical?
It's like 90 orders of magnitude. This big? No.
120.
Yeah. Yeah. I remember it's very. Yeah. It's insane.
Yes. So this is the largest ever.
Yeah.
Physics.
It's wrong.
Discrepancy between the theoretical prediction and the observational value. And yet, the observational value is not zero. No, it's not zero. So there certainly is something which is very, very fundamental. Nobody understands about this whole concept of dark energy, what it is, what it comes from. More on that in the last week or two of the semester. We'll speak about this much. Cool, isn't it? So I said that we're moving from here on to do more physics, but there's still be plenty of math. And right now our goal is to solve Einstein's equation. I mean, I could simply give you the solution, but you know it by now. So derive it on the board, so you don't have to believe me. Just have to follow all those indexes. Symmetry, yeah, mistake. So the problem is, how do we? The typical problem is, okay, we're given a mass distribution. Let's say it's in a vacuum, no mass distribution, zero, here. And we need to solve for that. So for that, we need to know the metric.
Yeah.
Thing is, even if we happen to know the Ricci, it doesn't tell us what is the metric. So how can we now? What is our best method of finding a metric that would be useful to solve? We must use some properties of the metric. The most important property that we can use is symmetry. So we need to find not just any metric, but metric which has symmetries. That is the purpose of what I'm going to talk about now. So that will be most of what we do today, but hopefully not all of them, because let's figure out we should. Well, I do owe you 2 lectures, because I was not here for 1 week. So if we won't have time, then I'll just have to add it. Yes.
So we can solve this equation. So we basically don't know. We know nothing about geometry. We just said we don't have any mass in space. But
Let's say it's an example.
yeah, and
So in this extreme case, that there's no mass.
but can space be curved if there is no mass?
Oh yes, because it can be. You can be close to a star. I mean, think of astronauts orbiting Earth. There is no mass around them, but they are still influenced by the gravity of Earth. You'll see. I can put
But
a point mass on Earth.
around. I mean, Earth is close to astronaut. The Earth effect.
Yeah, but
geometry
locally,
of
of
space.
course, but locally, T mu nu is 0 for the astronauts. Right? In the astronauts, in the vicinity of the, or you can think of the Earth as orbiting the sun. Right? Maybe this is a better
Yeah.
to visualize, right? Because we're quite far from the sun,
Yes.
yet we're influenced from it. So you know, if you look around us, we don't feel anything. There is no T mu nu there, but there is, of course, from the sun. But still, around us, there is nothing. this is supposed to a situation where you have continuous dust of particles everywhere, which is what we'll do in cosmology. We basically say all the stars, all the galaxies, we can treat them as continuous gas. Team you knew cannot be zero.
The solution, let's say something equal to zero is not unique because it's not in an equation.
Yes.
Oh, because zero is substitute.
Nothing between. Okay, but first thing first. So right now we're interested in looking at symmetries of the metric. Symmetries and Killing vectors. This is a comment. Killing it's not because there are particularly deadly vectors, but this is because of a German mathematician called Wilhelm Killing, who was the first to introduce this community. So it's named after him. So the question we have is something along. We'd like to use the symmetry. We would like to use the symmetry of the metric to get information. About it. But we still don't know the metric. We still don't know the metric. So what do we do? So what we really want is to write down the symmetry in a way which is coordinate independent. So it's independent of the metric. Symmetry. So we want to write symmetry in a coordinate independent let's say that our metric, not our metric, our manifold is the surface of a sphere. Right? Our beloved one, surface of a sphere. Now I don't have a ball. Let's say this is our manifold. Well, obviously it is symmetric. What do we mean by it's symmetric?
If you are changing by just a basic physics.
Exactly right. So if I'm in a point here, and I'm now transforming from this point to another point here, what happens to the metric? Nothing. It doesn't change. So if it's point x and this is x prime, then g mu of x is equal to g mu of x prime. Okay. That is intuitively what it means symmetric. Okay.
Can we just define the metric for whole manifold in this case?
Yeah, of course, I can define it in homework.
Yes,
I mean,
I'm
I'm looking now, yeah, but I don't need to. I'm just saying,
Yeah.
what does it mean that there is a symmetry of space? But if my space would look something like ellipsoid, like American football, and then if you go from this point to this point, you won't have that symmetry. The metric will not look the same. If you go from that point to that point, you will have the symmetry.
So you mean that sometimes we cannot define globally what is the metric, right?
The metric is defined everywhere in space. Just when I'm making maybe what confuses is the following. I'm making a transformation. What am I doing here? The metric is defined everywhere. I can select every point I select in that space, I have a metric in that.
Yes.
The metric, though, can vary. It can depend on the coordinates. It can depend on the position of the manifold. Right?
I mean, in this case, for sphere, it's dependent
In that sphere, it's not.
theta. It's sine squared theta.
Yeah.
The metric.
Well, that depends on the because this is a choice of coordinates, certain coordinates. Facility is same. So what we want to do is take a transformation. Take a transformation that maps manifold M to itself. So every point on M, for example, in this specific case, and every point M I'm mapping to another point on M. Right. So such a mapping of from point on the manifold to itself as a naming map. This is called, you may know, that's called isometry. This is called isometry. Here is me, and I can map, like we did the mapping from, showed it in, I think, in the tutorial. Mapping for point M to a different space. Here I'm pointing from M to itself. Every point in M is being mapped to another point in M. Right? That's called an isometry. It's just the name. For example, right? Promise you an example. Let's look at the simplest space, the Minkowski space. Example. Minkowski space. ds squared is eta mu, and dx mu, dx mu. This is minus t squared plus dx squared plus dy squared plus dz squared. Now, can you give me an isometry of this space? So any translation is an isometry. Right? So if I take a translation, x mu goes to x mu plus a mu. Give me some constant. Is an isometry in this space. Can you give me another isometry? Rotation is an isometry. So Moment transformation, x mu goes to lambda mu x mu. That's also an isometry. Basically, I'm mapping every point in space to another point in the same space. Yeah, not hard. And now you see that there is the metric here, eta, for example, is invariant under translation. If I'm changing x mu to x mu plus a mu, what's going to happen to the metric? Nothing, right? It's the same metric. And how can I see that right away? Because eta mu nu is independent on any of the coordinates. It's just a number. So eta mu nu is independent on x mu. That means that the metric is invariant under translations. Okay. Let's generate two statements. Let's say that we choose some direction which is specified by a vector in that direction. So let's say sigma. So this is d sigma. So directional derivative is a vector. Okay. So if whenever d sigma g mu nu is equal to 0, so the metric is not changed when we're making a transformation in this direction, it means that there is a symmetry. So d sigma g mu equal to 0 means that x sigma goes to x sigma plus A sigma is a symmetric. Okay? Concept should not be that difficult, I think. Now, before I'm going to fully derive the equation, there is a very important result of that. If I'm looking now at the motion of a test particle in that kind of, right? And if there is this isometry, so it's not changed, then the momentum of the particle along the direction of the isometry is not changed. Okay? So let's prove that.
It's just a consequence of the method.
You can look at it like that, but we're going to make a direct proof of that. So isometries and the motion of test particles. So I said, the momentum component is sigma of a test particle is a conserved quantity of motion along an isometry. So that's going to prove that. So remember that we showed that we can write down the geodesic equation. That's the equation that the tangent vector is always parallel to itself.
Sure.
Right? So, geodesic equation. Geodesic equation. Nabla u is equal to u lambda nabla lambda mu is equal to 0. From mu dx mu over the times. Is the tangent vector along the path. Okay. Choose the formulas. So that means that if this is the four velocity, we can simply write that in terms of p mu, which is just mu mu. So what's written here is p lambda nabla lambda p mu is equal to 0. Now we have the metric compatibility. Because we said that lambda g mu bounded size is equal to 0. So we can use that to lower down the p. Right? So if I use that, we end up with a p lambda d lambda. Now I'm expanding. So expand the y derivative. P lambda d nabla p mu minus gamma rho lambda mu p lambda p rho is equal to 0. Just lower it down and then expand. this is the change of the momentum of the particle along the path. So P lambda P mu is m dx lambda over the tau d lambda P mu to just m d P mu over the tau. First term is just the change of the momentum along the path. Now let's look at the second term. Gamma rho, over there, easier for me. Gamma rho lambda mu P lambda P rho means now I'm going to expand the gamma. So half G rho nu d lambda G mu nu plus d mu G mu lambda minus d nu G lambda mu. Then P lambda P rho. I can use the inverse metric to raise the index. This is 1/2 and d lambda G mu nu plus d mu G mu lambda minus d mu G lambda mu d lambda P mu. Now these are symmetric, right? P lambda and P nu are symmetric, right? Which means that this term I can exchange nu and lambda. Exchange nu and lambda, and this term will cancel with that term.
Okay.
This is equal to 1/2 d mu G nu lambda P lambda P nu. So overall, we get from here that from the geodesic equation we have m dp mu over p tau is 1/2 d mu G nu lambda P lambda P mu. Now so far what I did is completely general. I didn't do anything really crazy. Now you can see it right away. So now let's say that the metric is independent on one coordinate. Okay, so let's say if G mu nu is independent on the coordinate x sigma. What does it mean?
So sigma
D
G.
sigma G mu nu is equal to 0. Right. That means what? From here in this equation?
P sigma is just a constant.
Exactly. It means that dp sigma over the tau is equal to 0. Okay? Which you get straight. Okay, so it means that these isometries, right, the symmetries of the metric are extremely important. So now, I want to have a general description, and that's called killing the equation of killing vectors. General description of symmetries in vectors. first thing is that, okay, what we basically showed is that if the metric is independent on a component, then the momentum is conserved along this component. The opposite is not necessarily true. Metric can depend on the component and there will still be an isometry. Okay? The simplest way to see that, and we can write down, I'll give it to you as an example at the end, but just think of it for a second. If you write down the metric of a flat space-time in Cartesian in polar coordinates, then you find out that the metric depends on R, right? But there's still it's interesting. So yeah, so it's you have a more you need to have a more general way to describe that. So what we do is the following. We got that PB sigma over the tau is equal to 0. So let's assume that G mu nu is independent on one coordinate. It is independent on coordinate which I call here x sigma star to minus. This is the coordinate. Yeah, so we start with here and we want to promote that to something which is completely combined. Then we look at the vector that goes along this direction. We look at the vector which I call K after killing with V sigma star. So along the direction of this coordinate. And then each vector V is V mu D mu. So in component notation, we have that K mu, the component of K mu is D sigma star mu, which is a what? The K mu is D sigma star mu, which is what? K mu goes along one direction, sigma star. If I look at components, no, if mu is along sigma star, it should be 1. Right, so overall we get what? You don't see the right one.
Delta mu sigma
Delta.
star.
Right. Vector, I chose one coordinate, right? X sigma star. Okay. And I'm now looking at a vector K which is along this direction of sigma star. Right? So the components of this vector has to be delta mu sigma star. Okay? Now, generally we say that K mu generates an isometry. That's the standard notation. K mu generates an isometry. That's a technical way, a technical term. Did you learn about generators in general? Yes, like in group theory. You did. You did. Place where you're supposed to see that, but I think there is a problem here that is in course on analytical mechanics, rigid quantum motion. I think somehow this is being skipped here. So where did you see that? We took a course in math about group theory.
No,
It's my course? Which course? Elementary particles, yeah, it's there. Okay, so K mu generates an isometry, basically. Okay. So, using this vector, I can write the component of the momentum in the sigma direction, sigma star direction. The component of the momentum in the x sigma star direction. P sigma star. You can simply write it using this delta as a k mu p mu. Or k mu p mu, doesn't matter. So it looks covariant. Now, when we say that the momentum is being conserved along a path, that means that the directional derivative along the geodesic is zero, right? Obviously. So the covariant derivative, so conservation of momentum, means that the covariant derivative must vanish. So dp sigma star over the tau is equal to 0, which means what? That p mu nabla mu k mu p mu is equal to 0. The covariant derivative p over the tau is dx mu over the tau nabla mu. P mu is dx mu over tau, so now what is left is simply to expand that. So if we expand that, we get P mu nabla mu k mu P mu is what? So now we have to open the parentheses, so it's a P mu k mu nabla mu p mu plus p mu nabla mu k mu. What about this term? What is written here?
The change in the momentum should be 0.
Should be 0. Why?
Because momentum is conserved.
Geodesic equation, basically. So this is 0. So you're left with p mu nabla mu k mu, and we have a symmetry in mu and u. Right? So it means that the only symmetric part of this derivative is so I can take this derivative and divide it into a symmetric part and an anti-symmetric part, and only the symmetric part is a non-zero, because I can simply exchange mu and u. So everything anti-symmetric will give me 0. So that means that I can write it down as 1/2 p mu nabla mu k mu plus nabla mu k mu. So the conclusion is that every vector that is equal to 0. So every vector k that satisfies this equation, basically nabla mu k mu plus nabla mu k mu, or k mu plus k mu is equal to 0, implies conservation of k mu p mu 1 nabla mu k mu plus nabla mu k mu is equal to 0, that means that p mu nabla mu k mu p mu is equal to 0. Okay. Now this has a name, this equation. This is called Killing equation. And the vector k has a name, this is called the Killing vector. Or clearly vector field. Now, one last thing which will appear in your homework that you're supposed to get today, you will get today, is that in two or more dimensions, there are more Killing vectors than dimensions. Which sounds counterintuitive at the first moment. Then when you think of it, so it actually works out. Because the Killing vectors are not defined only at one point, but along trajectories. Okay. Now, let's give you an example. Questions about it? And greater or equal to two dimensions, there are more Killing vectors than dimensions. So example. 3D Euclidean space. Okay. What is the metric? What? Unit. Okay. All of the metric components are independent of x, y, or z, right? The metric components are simply 1, 1, and 1. Right? So they're all independent on x, y, and z. So the first three Killing vectors. Killing vectors. It's 1, 0, 0. Y mu 0, 1, 0. Z mu 0, 0. So in each direction I go, there is a symmetry. Nothing changes. This is not the all. I have other Killing vectors here. I have more than 3 Killing vectors. What else can I do?
You can add them.
I can make a rotation. Okay. How can we say that? I can take the same metric. There are more than one way, of course, of seeing that, but this is associated with translations. This is the Killing vectors associated with translations. Now I can write the same metric, right, but in polar coordinates. Then the metric will look like bs squared is dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So what is the metric components independent on? On phi, right? They depend on r, this is 1, and they depend on theta. But they're independent on phi. Right? So what would be a killing vector?
Phi.
D phi is a killing vector. Right? So a vector in the direction of phi. Right? So if I translate that back to Cartesian, this is a what? R is a minus y dx plus x dy. So what will be the killing vector? If I write it in that component that way, yeah? Be
minus y,
minus y,
x, and z.
x, and z. That's not a killing vector. Right? That corresponds to what?
Rotation.
It's rotation around the z-axis. Right? It's obvious. Of course, this was a completely arbitrary choice of the z-axis. Right? We can do rotation around the x-axis and the y-axis equally well. Right? So get other two killing vectors. So this would be r mu, s mu, so it would be z 0 minus x, and t mu is 0 z minus z and y. So you got the idea? So three-dimensional, but we have more than 3 killing vectors. There are 6. Okay. How are we doing some time? Good, we have time. So get homework today now. All right. Any further questions about killing vectors? Just put a note. It's in my lecture notes, which I'll post them on. Of course, the subject of killing vectors appear in any standard textbook in general relativity. It turned out that I've seen the derivation of the killing equation in more than one way. What I derived to you now is what I thought would be the most intuitive one, but if you go to other textbooks, you'll see different derivations of the same equation. Of course, all end up with the same equation. I put in my lecture notes another derivation, which I can skip now because I don't think it will add much to the discussion. Right. If you didn't fully follow, then you can simply look at another derivation, or as I was telling you, just go to the textbooks and read it in your favorite way. All right, good. I'm quite happy because we saved some time to basically move on to actually start to solve Einstein's equation. So what we're going to do now is to start by looking at solutions to Einstein's equation. And the solution we're interested in, of course, is called the Schwarzschild solution. Schwarzschild have a great name, which is always difficult for me to spell. Schwarzschild solution. And this will lead us to the concept of black holes. So it's a solution, so it's a solution to Einstein's equation. So what I said, the solution we're going to look for is a solution in vacuum. So we look for a solution in vacuum. What do we mean by vacuum? There's no t. So t is equal to 0, meaning that the equation we're looking to solve for is r mu nu equal to 0. Now, I don't know if you know the story, but it's a historical story. Karl Schwarzschild was a mathematician. So Einstein wrote down this equation, published it in 1915, and Schwarzschild found the solution fairly shortly afterwards, in 1916, in order to publish a solution. But as you know, this was the time of the World War I, so like every young person, he was called for the army, and he got wounded, and then shortly afterwards he died. So, fortunately, he got the solution, but he never lived to see how much we could use the solution. The solution in vacuum, R mu is equal to 0.
Maybe T?
No, R mu is equal to 0. T mu is equal to 0, and then Einstein's equation would mean that R mu is equal to 0.
What happened with which scalar?
What happens with which scalar? R mu is equal to 0. What happens to 0? Okay. That solution describes basically a spherically symmetric vacuum spacetime. I already said we already know the solution of Minkowski, but it's less interesting. I don't want to generalize it. And the thing that is important, because it is confusing, and I remember that myself was confused in that when I was studying that the first time. Vacuum means in the vicinity, basically there is no mass everywhere except for one point which will affect what you'll see.
אנשים אומרים שההקלטה של ההרצאה מקטירה.
I have no idea about the technicalities here. And I tell people to come here and sit down here. I don't know. Okay. So we also said that the Einstein's equation is nonlinear, meaning that the real problem is to get a solution. So once we think we found a solution, so what does mean a solution? Finding a metric, G mu nu. This is the solution we do. G mu nu, that we plug it into Einstein's equation and we get that. This is Einstein's equation of vacuum, and the solution meaning G mu nu. There is a theorem, which is called Kirchhoff's theorem, which states that Schwarzschild solution is unique. It's a unique spherically symmetric solution to Einstein's equation in fact. That is called Kirchhoff's theorem. Write his name properly. Kirchhoff theorem states that Schwarzschild solution is a unique spherically symmetric solution to Einstein's equation in vacuum. In fact, the way I'm going to derive Schwarzschild solution is very much following the proof of this theorem, because we're going to build it from zero. There is one last bit which I'm going to skip because I'm lazy. So I'm not going to give you the full proof of Kirchhoff's theorem, but only like 90% of the proof, which will be given by the way we construct it. So what we're going to do now is deriving Schwarzschild solution. Okay. So what we look for is a solution that is static and isotropic. So we said spherically symmetric. So there is a source of gravitational potential at, let's say, the beginning of the coordinates at 0, 0. Right? And the rest there is none. Okay? It's all empty vacuum. And so what we're looking for is a solution that is static and isotropic. We look for static and isotropic solution. What do we mean by static? Doesn't change in time. What do we mean by isotropic? Yeah, it doesn't change in directions, in angles. Okay? Everywhere we look, it's the same. So if it's isotropic, what's the best coordinate to describe it? Spherical, obviously. Polar coordinates. So from that, we decide to use polar coordinates. So I'll just write down the omega squared is the theta squared plus sine squared theta d phi squared. That's all. Of course, it's a 4-dimensional space-time, so we need to have two more coordinates. It's a pattern phi. And right now we want to use very general form. So add two general coordinates. This would be call it T prime, which is A, and R prime, which is B. This is still not related directly to the time R that we used to think of. So the metric, the most general form of the metric, look something like ds squared is the GAA of A and B, dA squared plus GAB of A and B. Let's say dA dB plus dB dA plus GDB dB squared plus, here I can think of R squared of A and B. R is just a function of A and B, d omega squared. Okay. Right now R is not an independent coordinate, but it's some function of the coordinates A and B. Okay. It's a general solution. So from, we don't want A and B, let's work with A and R. So from A and B, coordinate change. I should explain it better. We have these cross terms, right? The ADB, the BDA. We didn't say that they have to be exchangeable. Of course, we don't like that. We want to have something which is, we don't have these cross terms. So let's see how we get rid of them. So the first thing we do is the coordinate change from A to B to A and R. Again, something which is can be done in a general way. How do we do that? By inverting our invert R. So I have ds squared is a GAA of now A and R. dA squared plus GAR of A and R. BA BR plus BR BA plus GR of A and R BR squared plus R squared d omega squared. Okay. Everything is done mathematically, so there's no good question. Now, the next step, I said I want to get rid of these things. So I want to find a new function, which obviously I'm going to call it t, which is a function of a and r. And such that there will be no, so I want to change a to t, such that in the coordinates t and r, there are no cross terms. No cross terms. The form dt dr plus dr dt.
Basically, you're trying to diagonalize.
Yes. Now I can write down dt as dt dA plus dt dr dr. So t is a function of a and r. Okay, that is perfectly legitimate, which means that dt squared is equal to dt dA squared plus dt dA dt dr dr plus dr dA plus dt dr squared dr squared. So we don't want this cross term here. This one we don't want. So what we really want is to replace these three terms with something that looks like, we want to have something that looks like m dt squared plus n dr squared. M and n are some functions, which are not specified yet. So, which means how can we do that? Actually, quite easily. We have m dt dA squared. M dt dA squared is what? This is the GAA. Right? GAA squared. And then n dr squared, so we have n plus m dt dr squared is equal to gr, and m dt dA dt dr is this gar. So I have three equations, three unknowns, t. Three unknowns that we have is the t, which is a function of a and r. And then m and n. Three equations, three unknowns, there is one single solution. Okay, with me?
Why are you saying there is one single solution? It's non-linear equations.
Sorry?
Why are you saying there is one single solution and the equation is non-linear? If we have שלוש נעלמים,
No. The nonlinear is for the full solution.
Okay.
This one, there is a full. I mean, I determine these unknowns as functions of GAA, GR, and GAI.
Ah,
I didn't say what they are. Just say it's a general solution. So what I just showed is that instead of that, terms here, I can replace it such that I'll write down the metric as a ds squared is just m of dnr dt squared plus n of dnr dr squared plus r squared dx, which is what I want. Okay. I did not yet specify. I just said t himself can be a function of a and r, but I don't know what it's saying. Just say that most generally I can get a static and isotropic solution. The most general form, I can bring it to this form, where m and n are some functions of t and r. And I did not say what are t and r, I just said these are coordinates. Right. I didn't specify whether they are, how are they connected to what we call time or values. So it's completely mathematical derivation. Of course, we do want to give them some physical interpretation, right? So we know that although everything here is symmetric, at the end we'll have to break this symmetry. Especially if we go to r goes to infinity, we should end up with cosine. It's called asymptotic flatness. Okay. Just want to make sure that everybody is with me, right? The vacuum solution means I put some mass at r equal to 0, like a point mass at r equal to 0, and I'm looking at everything everything else is empty. Basically like a delta function of mass in space. Okay. And then everything else is empty, and I'm looking for a solution to this equation. Of course, when I go to r goes to infinity, I get back in Minkowski because the mass is too far away. I know nothing about its existence.
You're basically trying to find the Green's function for Einstein equation.
You can look at it like that, but I don't think anybody. I never saw anybody calling it like a Green function. Okay. So asymptotic means r goes to infinity. The metric. This is the first time that we are introducing some physical intuition into the calculation. Approaches and cosine. Approaches and cosine. Which means it must have one negative and three positive eigenvalues. Right? And how do we call that? Pseudo-Riemannian. So, one negative, three positive components. This is called pseudo-Riemannian. So we can choose m to be a negative function and n to be a positive function. That makes sense. How do we choose that? Replace m and n with new functions, alpha and beta, and write down the metric as ds squared being a minus e to the power 2 alpha of t and r dt squared plus e to the power 2 beta of t and r dr squared plus r squared d omega squared. Okay. That's why I'm ensuring that this is always negative, this is always positive. Okay, again, everything we used here was just saying, okay, this is the most general solution for a static and isotropic, namely spherically symmetric solution. the most general expression. Have in mind what we didn't do. We didn't even make any attempt to solve Einstein's equation. Just wrote down the most general static and isotropic solution to Einstein's. A metric that describes spherical symmetry. Yes, has a spherical symmetry. Now remembers the time. Well, the rest is actually this is a reasonable place to stop here because now we have to dirt our hands basically, and now we have to take this solution and plug it into Einstein's equation. Basically calculate now the affine connection, and then calculate for the affine connection the Riemann tensor, and then contract the Riemann tensor to get the Ricci tensor, and then see that it equates to 0. And what we get when we do that?
Two differential
Get
equations
the values of alpha and beta. We'll tell us how the metric looks like.
and goes to infinity, alpha and beta should vanish.
Yes. We'll see. All right. More questions? I think it's a good time to stop then. So now on Sunday, obviously there is a holiday, right? So we'll have lectures. So we'll meet again in 1 week. We'll get homework for next week, so we'll have something to do over the holiday. And yeah, as I promised you, what we're going to do from here on basically is to look for solutions and discuss the solutions of Einstein's equation. So we're sort of halfway of the evaluation of the solution. We'll get there next lecture. Any further questions? Okay. So have a nice holiday and a nice weekend. We'll see you in 1 week.
יש לי שאלה קצת כללית. כאילו בדרך כלל כשאנחנו נתקלים נגיד במהלכים קשים, אנחנו מעבירים אותם במרחב הטבע, ואז אני אאלגר את זה פשוט. למה פה לא עושים את זה? משוואות דיפרנציאליות כאילו חלקיות שהן נורא קשות,